This section is about convolutional operation. Specifically, we will learn what are the filters, what is the convolutional operation, and 2D convolution at the end. Image filtering is not a new technique in image processing and computer vision, and filters are widely applied in this domain for many years. Filtering is a technique for modifying or enhancing an image. For example, we can filter an image to emphasize certain feature or remove other features. Image processing operation implemented with filtering include different tasks and jobs. For example, we do it for the smoothing, sharpening, and edge enhancement. By applying filter, we change the range of the pixel value of image. Therefore, the color of the images can be changed without changing the pixel position. In this figure, we can see an example of image filtering. The goal of using filter is to modify or enhance image properties in order to extract more valuable information, such as edges, corner, and blobs. There are multiple ways to do edge detection. Here we will present a sample operator. The sample operator uses two 3x3 kernels or filter which are convolved with the original image to calculate our approximation of the derivatives, one for horizontal changes and another one for vertical. Now question is why should we calculate the first degree of the derivative? The reason is edges occur when the intensity of our neighboring pixel changes fast. Therefore, approximating the gradient of the intensity of each pixel can show us the edges, right? Okay, if we define A as a source image and Gx is an image uh, which at each point contains the horizontal derivative approximation, where the computation is as follows. Here, in order to calculate this, we have a 3x3 kernel, -1, -2, -1, 0, 0, 0, and then +1, +2, +1, where we convolve it with the source images. Here, the star indicates the mathematical operation as a convolution, and which is different from conventional matrix multiplication. And if we look at this 3x3 matrices, it contains indeed the uh, two filters, right? We have here the averaging, and also like here we calculate the averaging, and also applying here we indeed calculate the differentiation. Like we can extend our explanation for y dimension as well. Here, similarly, the gradient of the image gy can be approximated by like now we have another 3x3 kernel -2 -1 0 +1 -2 0 +2 -1 0 and +1 convolving to the source images. Here in order to get at the end the gradient images, we need to calculate the square root of gy square. And this matrix operation were used to create the filter picture of the Einstein, which you saw previously in the right side. And here is another interesting example which show us when we have when we calculate only the vertical edges and the vertical edges they detected in the using the SX, and versus when we calculate the horizontal edge in a y dimension. And here is another, and this is a combination of the both Sx and Sg, where we calculate the root square of gx over gx square plus gy square. Let's continue with another example. Assume we have these input images. Now, this is our source image or A. We would like to calculate the subtle operator on the top of these input images. But before that, let's see how we can, how we really represent these images. Well, in this case, we have a grayscale images where at each pixel at this image has a value between 0 till 255. They are integer, where we show the black pixel with the 0, and also the white pixel are represented by 255. We can show these input images as a like a matrix. For example, in this case, we have 10 by 10 matrix as a represented for this input image. As we saw earlier, by moving Sobel filter on the top of input images, we are able to detect the vertical edges. By moving a Sobel filter on the top of images, indeed we calculate the g of x because we have s of x, x dimension. Indeed, we convolve the each position of the images with the Sobel operator. For example, if we consider this position, here we need to calculate like a dot product of these two matrices. Like for example, here we have a minus 1 times 0, 0 times 255 plus 1 times 255 minus 2, 0, and similarly for the other other also position, we can calculate the g of x. And by applying a Sobel filter at each location and every location, then at the end we will have the input matrices by 10 by 10, and which we call this feature map. And in order to get these values in the same range, we normalize this feature map. By normalizing the feature map, we will have these values, and we can see the vertical edges here in this figure. Another important point is, if you remember, our input image was with a size of 10 by 10. By applying a Sobel filter with a size of 3, our output is in the size of 8 by 8. Here we actually did also kind of dimensionality reduction compared to the input image. Now you may ask, why do we need to know all of this, right? Like indeed, all which I discussed and introduced so far, these are like an introduction for convolution operation. Okay, what we just did was exactly extracting a predefined feature of our input. For example, we move a Sobel filter on the top of input data, and then we detect the edges. This is what a convolutional neural network does almost. Okay, they extract the feature from the input. But the big differences here is, well, we usually do not tell the convolutional neural network what to look. Okay, they decide itself. Okay, it's a learnable parameter, and they learn by themselves. Indeed, there we initialize lots of random filter or weights and apply them to our input. Then a classifier, which can be, for example, a feed-forward neural network, use them as input data, and filter entries will be adjusted by a common gradient descent method during the training process. Again, what so far I explained is like we have the input dump images. We apply some Sobel filter, which we already knew the values for each, in this kernel values. And then by applying this filter on the top of the input data, we created the feature map. But what's happening in a convolutional neural network is quite different. We have input data and we initialize a random kernel or filter, and by applying these filters on the top of our input, we will have a feature map. Just another point here, the values for the for the each like a filter or kernel is not given, okay? But in a Sobel filter, for example, we have some predefined value for Sobel operation. But for the other kernel which we use usually in a neural network, we do not have any values, and this value can be initialized in the beginning of the training process of a certain a strategy and learn algorithm, but they are a learnable parameter, and they will update during the training process. Okay, before continuing this topic, I will introduce you some basic definition. Because we are working with images, it's good to know what is the gray scale image means. Indeed, the gray scale image is a matrix with a dimension of the height, width, and here we have one as an input channel. And here are between the 0 till 255, where the 0 is for black and 255 is for white pixels. The color full images, here we have our matrices has a dimension with the height, width, and tree. Here we have a three different input channel, and where the tree is the depth of the images, and we have here the size of the depth of tree means we have a three channel for red, green, and blue for short RGB. And it's important to know a filter depth is always equal to the input depth, okay? For example, if we have color images, then our filter depth is equal 3, and when we have a grayscale as an input, then our filter depth is equal 1. And filters are a square, therefore we only need to say one integer to define their size. When we say, okay, subtle filter is with the size of 3, means it is 3 by 3. Or for example, when we say a filter of size 2 applied on a color image, means we have a 2 by 2 kernel 3 times, because it is the depth of the RGB image is 3. Let's look how does the 2D convolution work. Suppose we have the input size of 3 in 3 with one input channel, and this actually our input has a value of a, b until I. We have a 9 value for our input. And then we have also filter size of 2, and we would like to apply this filter on this input image, for example. By moving the filter to the first spatial location, we will get the first entry of our feature map. But how does it actually calculate? It's like this. We get the dot product of the filter and also the value of the input images. Well, here is, for example, the pixel value if it is image. Therefore, we calculated also similarly for other also window as well. And similarly, by moving the filter to the next spatial location, we will get the second entry of our feature map. Similarly for the third one, and at the end, we will have the 4 values for our feature map, as you can see here, calculated by 2D convolution. More generally, if we have the input matrix of I, and having a W as a filter or kernel, therefore we can actually define the each input of our feature map similar to this formula. We can have a sigma of the M. For each value of the entry, we calculate I plus M minus 1 and J plus n minus 1 times WMN. Here the WMN denotes the image size and kernel size respectively.